Hello, you are most welcome. I'm teacher Ivan from Wuna Educational Services. We are still looking at the A-level Physics 1 calculations, and in particular, we are looking at the calculations from heat transfer. Under heat transfer, we started with conduction. And now we are here trying out numbers that require us to use the formula for the rate of heat transfer. We have so far looked at two examples. Now we are going for our next examples. Example number 3 tells us to calculate the amount of heat conducted through 2 meters squared of a brick wall that is 12 centimeters thick in 1 hour if the temperature on one side is 18 degrees Celsius and on the other side it is 28 degrees Celsius. But the thermoconductivity of the brick is given to us as 0.13 watt per meter per Kelvin. So from our equation, we shall substitute for what we are given to get what we want. But the question is asking for the quantity or amount of heat conducted, and therefore from this equation, the quantity of heat is Q. Q is representing the amount of heat, but when we divide Q by T, it becomes rate of heat transfer. So meaning that for us to remain with the amount of heat, we shall multiply by time, so that we end up with our heat as the thermoconductivity times the cross-sectional area times temperature difference times the time over the length. In most cases, when asked to get the amount of heat, we must be given the duration for heat transfer. And from our question, we are given everything, so we shall just substitute. We are given the thermoconductivity as 0.13. We are given the area as 2 meters squared. We are given the two temperatures. Then we are given the 1 hour as time. And then we were given the thickness as 12 centimeters, so we convert to meter. That's why you have exponent -2. Otherwise, when we simplify that, we end up with our heat as 1.56 exponent 5 joules. So that is, but it is very paramount for you to always first summarize the information while converting those quantities to their SI units. Okay, so that has been the calculations that involve the use of the rate of heat flow. Otherwise, we shall look at the heat flow through several surfaces. We have majorly 3 arrangements of surfaces whose rate of heat flow is considered and is different. We shall start with surfaces that are arranged in series. A good example of the series arrangement is when they are building. The way they arrange the bricks, they arrange them in a line. So when you put one after the other and you let heat go through one by one, from the first one to the second one to the third one, that is what we call the series arrangement of surfaces. For instance, they told us to consider 3 plates, that is PQR, of thermoconductivity KP, KQ, KR respectively, whose ends are maintained at the temperatures theta 1, theta 2, theta 3, and theta 4. This is our illustration for that, where this is plate P, plate Q, plate R. They are arranged in a line one over the other. And when heat is entering, coming from one side, it first goes through the first plate, enters the next plate, and the last plate like that. So it does not go through the plates at once. That way, we shall have what we call the series arrangement. And therefore, we assume that there is no heat that is lost to the surrounding, meaning that the rate of heat flow, or the rate at which heat entered the first plate, will be the same rate in the two other plates. And that means that the rate of heat flow will be maintained constant. And that's why for such an arrangement, we are saying that the rate of heat flow at the entrance is equal to the rate in plate P, is equal to the rate in plate Q, and is equal to the rate in plate K, and is equal to the rate at which heat will leave the surfaces. So, therefore, as we summarize, for series arrangement, the rates of heat flow through each surface are equal. The rate of heat flow through the first, the second, the third are equal. That is on assumption that no heat is lost to the surrounding. Let us look at some of the calculations where we apply this. So this is our number one. In number one, we are told that a sheet of rubber and a sheet of cardboard, each 2 millimeter thick, are placed together. To place is to pack them together, squeeze them together, and their outer faces are maintained respectively at 0 and 25 degrees Celsius. If the thermoconductivities of rubber and cardboard are respectively 0.13 and 0.05 watts per meter per Kelvin, therefore, they want us to find the quantity of heat which flows in 1 hour across the composite sheet of area 100 centimeters squared. So, please, when you want to carry out this calculation, first of all, summarize the information, converting the quantities to their SI units. For instance, we are given the thickness, that is L, in millimeters. We shall convert this to meters. We are given the temperatures. For the temperatures, we shall leave them because we are looking at the temperature difference. And it is the same whether you convert or not. That's why we leave them. And then we are given the thermoconductivities. We are given the time. Time is an hour. We need to convert them to seconds. We are given the area in centimeters squared, so we need to convert it to meters squared. And then, since they were placed together and their faces, how do we tell that that arrangement was series? When they tell us that their faces, their outer faces were maintained at 0 and 25. Meaning that at 25 is where heat was entering from, and at 0 is where heat was leaving from. So, and this is our illustration for the question. whereby we have two sheets, that is for rubber and for metal. Sorry, for rubber and cardboard. So assuming this is our point of entry for the heat, and at that point the temperature is 25. At the interface where these ones are joined, the temperature is theta because we don't know it. And at the other outer surface, it is 0 degrees Celsius. So since they are arranged in series, we shall therefore equate their rates of heat flow. So when we equate, we substitute. On substituting, we shall get the temperature at the interface. Remember, the question is asking for the heat which flows in the composite sheet in 1 hour. But you cannot get that heat without getting the temperature at the interface. So after getting the temperature at the interface, we are now going to substitute in one of the two to get the rate at which heat flows. Why do we substitute in one of the two? Because the rates are equal. And that will give us, when we substitute, after getting the temperature, we shall substitute and get our final answer. Remember, from that formula for rate, we are multiplying through by time. So that instead of having rate of heat flow, we now get the amount of heat flow. So when we make it to the subject and substitute, we shall end up with 1.64 exponent 4 joules. So that is our first example on surfaces in series arrangement. Otherwise, we are still looking at more examples under series arrangement of surfaces. I'm teacher Ivan from Wuna Educational Services. Please, I request you to subscribe to our YouTube channels, follow us and like us on Facebook, TikTok, Instagram, and X, so that we learn together at convenient time, at the convenient place. Otherwise, hope to see you. Bye-bye.